Alright, so in previous video, I gave you guys two questions to think about, right? So the first one is, which elbow angle is more effortless holding that dumbbell? Would it be like this, like parallel to the ground, or it would be like with a certain angle? Which condition will make it easier to hold a dumbbell? That's the first question. And the second question is that if we move the bicep attachment site from proximal to more distally, how would that new attachment will affect the muscle force? So to answer these two questions, we need to understand the mechanics and physics of this kind of motion. So everything starts with torque. So if you remember in lab 5, we tried to calculate the height of the center of gravity when lying on the board, and we're using torque to calculate everything, right? So here we're using the same concept. Torque equals to force multiplied by the moment arm. And the definition of moment arm is the perpendicular distance between the axis of rotation and the force. So in this case, the moment arm will be the length of the stick if we're pushing here with the force. So the torque in this case will be F times R. But what if there is a certain angle, so the force is not perpendicular to the stick? If you remember, the definition of moment arm is the perpendicular distance between axis of rotation to the force. So in this case, it's this R. It's not a D here. So it's no longer the distance of the stick. It becomes this length, which is D cosine theta. Right? So here is D cosine theta equals to the moment arm. So the torque in this case would be D cosine theta times the force. And we know that R will be less than D, right? Because cosine theta is always smaller than 1 or equal to 1. So in this case, the torque is actually less than the torque in this case, assuming the same force. All right, so that's the concept of torque. And how do we use this concept to solve the question we have? Let's start from a free body diagram. So in the first video, you see how the equipment looks like. There's a stand here, and we have our upper arm and our forearm, and holding certain weight here. So to start drawing a free body diagram, the first thing is to list all the forces, right? So the easiest one would be the gravity of the forearm itself. So without holding that stuff, the forearm won't have its own weight anyway. And then if we're holding something, the thing has its own weight. So it's W of the forearm and also the force of the object. And because we're talking about torque, right? So we need to find the moment arm in this case. So the moment arm of this force generated by object you're holding will be this length, the green one, which is L cosine theta. All right, and also assuming the center of gravity of the forearm is in the middle, so the moment arm will be half of the whole green stick. So the moment arm of the forearm will be this one. So we can list all the clockwise torque, right? So clockwise torque would be F times L cosine theta, which is F times L cosine theta here. And also the weight of the forearm times 1 over 2 L cosine theta. So it's half of the moment arm of this force. So that's clockwise torque we have. But if there's only clockwise torque, the system is not stable, right? So it'll rotate this way. But actually, we're trying to hold the object, so we need certain muscle force here. We're applying muscle force by assuming the bicep, so we call it Fm. And we need to find its moment arm in this case, and we call it C here. And the muscle force is pulling toward this direction, so it's generating a counterclockwise torque. And that'll be Fm times C, force times moment arm, right? Force times moment arm. All right, so we have all the clockwise torque and all the counterclockwise torque. If the system is stable, so we're holding the dumbbell, it's not moving anywhere, so these two things should equal to each other, right? So Fm times C is a torque generated by the bicep, and that's the effort from you. And the load is generating certain clockwise torque by the object you're holding and also the weight of the forearm. So that's the load, and here's the effort. All right, so by solving this equation, you can understand like each component in the equation. So let's start from our first question. Which elbow angle is easiest to hold a dumbbell? So in this case, on the left side is holding a dumbbell with more parallel angle to the ground. In this case, we raise our forearm a little bit to make it steeper. Sorry. So from here to here, what changed? All right, the force didn't change, right? F is still here, W is still here, but the moment arm decreased a little bit, right? Because it changed from theta to theta 2, and theta 2 is higher, so cosine theta 2 would be a smaller number. So L cosine theta 2 would be smaller than L cosine theta here. And you can visualize it like the distance is shorter here. So if we decrease the moment arm, the load would decrease. So you no longer need that much muscle force to hold the dumbbell. So you need less force, which make the task easier. So in this case, it's easier to hold a dumbbell with steeper angle. So actually you can see from like this guy's facial expression, it's harder and it's a lot easier. All right. So I'm sure like Dr. Smith has talked about 3 class levers, and think about which class is the system we have here, or the system you have in your elbow with bicep. So the effort is your muscle force, right? And the load will be the object you're holding. So it's axis of rotation, effort, and load. So it's 3rd class lever system. Okay. And the second question is how muscle attachment affects muscle force, assuming we're moving your attachment site from here to here, more distally. What will happen? So here is a free body diagram of that kind of tendon transfer procedure. We move the attachment site more distally here. So I can visualize that the red line is actually longer, right? So actually the moment arm of your muscle force became longer. So C increases. But the load, assuming we're holding the same object, so the load is the same, and your weight of your forearm is still the same. So the load here is the same, but if you have larger moment arm, then you don't need that much muscle force. So the muscle force will decrease. Right? So if you move your tendon here, then you can generate less force to hold the same weight of the dumbbell. All right, so that's the answer of these 2 questions, and we're assuming to see the same phenomenon in our data. So with like steeper angle, we're assuming you'll see less muscle force. All right, and with more distal attachment site, we're assuming to see less muscle force as well. So that's about the free body diagram. And for assignment, as usual, a PDF or Word document. And you need answers to all 12 questions. And you don't need to attach the table because it's already given. And I will highly recommend you to type the answers. So it's easier for me to read it. And also, you can just create a new Word document and label the number of questions. So you don't need to really retype the questions. Just like label question 1 and here's your answer. I understand that. Okay, so let's see data collection in following 2 videos, and have a good time with this lab.